Hey, hey, hey. Welcome, everyone. Good day. Thanks for taking a couple of minutes out of your time to hang out with us here today. Just before we get going, some quick touch points. My name is Nik Alleyne. I'm currently a Director of Business Development at Serious Computer Solutions. I work primarily with the team that supports the Managed Security Services business unit. Along with that, I am also the author of 2 books, one of them being Hack and Detect, as well as the other being TShark, Mastering TShark Network Forensics. In my spare time, I blog at securitynik.com. Right, my blog title is Learning by Practicing, where we do lots of demos and give you the opportunity to be able to learn things from a practical perspective. Along with that, I'm a SANS instructor, teaching both the SEC 503, the Intrusion Detection in Depth class, as well as the 504, Incident Handling, Hacker Tools, Exploits, and so on class. So a lot of what we will talk about today is going to be basically surrounding content that we discuss in the SEC 503 class, which is the Intrusion Detection in Depth class. Additionally, we will learn a set of different things. We will look at some threat hunting. We will look at how we understand packet headers. We will dig into those packet headers. We will profile the threat actors. We will look at stimulus and response. And do note, this is now part of a 9, or what we hope might be a 10-part series. A lot of the content for the 9-part series is already there, but I'm hoping to round it off to a 10-part series. Today's session is also very practical. So what I would like you to do is go to my GitHub page at SecurityNik, right? You go to GitHub, SecurityNik, and if you click on this repository here, you will get to a list of files. And Stephen, I have Stephen in the background that is going to be providing support to me. Stephen, can you share the SANS TCP/IP TCP dump cheat sheet with the group? Once you have this, right, once you click on this link, you will see this file here. This is the SANS cheat sheet. It is what we will be working with as we learn about the ICMP protocol today. Later on, we will take advantage of the other ones. Along with that, we will need the PCAP file for the analysis. If we go here and we type nmap_sn, right, we will see this PCAP file here, and Stephen will drop that also. And once we download this file, we now will have the PCAP that we need to perform the activities today. Once again, this is fully hands-on, and you get an opportunity to practice various things, learn a couple of tips and tricks as we go along. So I will just give everyone a quick minute to get that together, and then we will start with the scenario. All right, let me keep this here, minimize that, and here we are. So I already have those 2 files, right? I have the PCAP file, right? If I say file, nmap_sn, we can see that this is a packet capture file. And we also have the SANS TCP/IP TCP dump reference guide. This is going to be important for us today. So here's the scenario. You are the new guy or gal that has joined the cybersecurity team of your organization. And the senior folks basically have assigned you your first task to perform. That task is basically to do some threat hunting. Threat hunting being we want to prove or disprove a hypothesis. The hypothesis being that the senior cybersecurity folks believes that that reconnaissance was performed against the organization. Now, before we get going into the deep, let's be clear. When we talk about reconnaissance, there's reconnaissance from 2 different perspectives. 1, active reconnaissance, and 2, passive reconnaissance. For us, our focus is on the active reconnaissance. Passive reconnaissance is those situations whereby the threat actors are gathering information about us online without us even knowing that they're doing so, right? For us, we're more focused on the active reconnaissance, where the threat actor is interacting with our environment, maybe using tools against our environment that ultimately provide some type of stimulus and ultimately maybe get some type of response. Okay. So how do we move forward now? We are the you or I basically represents the newbie on the team, and we need to prove or disprove the theory that there was reconnaissance performed against the infrastructure. So the team comes and they give you this nmap file here, right? Not this nmap file per se, but this pcap file. What is the first thing we do? Well, let me clear my screen here. Anytime you get a pcap file, the first thing you should do is run a tool such as capinfos against it. See, capinfos, and I will give it the file. All right. What this does is it gives me some basic information about this pcap file. So we can see here the file name, file type, and all of that. We see the encapsulation. Most days, your encapsulation is more than likely going to be Ethernet. We will see why this encapsulation instead says Linux cook mode. Along with that, we see the number of packets in this pcap file. We see the file size. We see the duration of the capture, and we see the first packet time and the last packet time. Why is this important? Well, remember, we are trying to prove or disprove a hypothesis via threat hunting. And the team comes and they give you this pcap file. They did not tell you when this activity occurred. So let's say it was a case where they said this activity occurred in 2017. You can immediately look at the first and the last packet time and conclude that this here is more than likely not going to have the traffic that you're interested in. So you can probably just send them back on their way to get a pcap file that actually reflects the traffic that you intend to capture. So at this point, since they did not give us a start and an end time, we are going to continue with our analysis. Now, once again, we see number of packets 437. We see the encapsulation as Linux cook mode. Just to help you understand a little bit more about this Linux cook capture mode, and when you're using, in Linux, basically, when you're using TShark or TCP dump, etc., let me clear the screen. You have the ability, let me see, okay, let me do this. You have the ability to capture on one or more interfaces. List, let's say TShark, list, INTR, FACS, right? You have the ability to capture on one or more interfaces. On most days, you might choose to capture on Ethernet 0, or maybe the Ethernet interface has a different name or so on. But anytime you choose to capture on the any interface, this is where that Linux cook mode comes in. This is basically a fake header, not your typical Ethernet header or anything like that. And we will see this header shortly. So we now have the pcap file, we know the duration, we know the number of packets, and so on. The next step for us is, and I will clear this screen by pressing Ctrl-L. The next step for us is we should look at the protocol hierarchy, the statistics of the pcap file to get some insights into what might be going on. So what I can do, I can say TShark, and I'll say -n, right? Because I don't wish to resolve the IP addresses to host name. Then I say -r, and the -r means I would like to read traffic from a particular pcap file. Okay, I'd like to read traffic from a particular pcap file. And what is the name of that pcap file? It is nmap sn. Now, along with that, right, if we just run this here, we will have traffic that flows through. But the focus for us is trying to figure out whether or not ICMP packets are in here, because the team came and they said they believe reconnaissance was performed via a network ping sweep. Now, you might be asking why a network ping sweep. Let me clear the screen here. The reality is most threat actors that are targeting your environment are more than likely going to perform a ping sweep first. This allows them to identify the host or hosts that are listening or that are alive in your environment. And once they identify those hosts that are alive, they can maybe write that information to a text file that will then be used as an input to some other tool. So look at it a different way. Rather than scanning every host, performing a SYN scan, for example, on every host in a /24 network, the threat actor might just perform a ping scan, identify maybe 10 or 20 hosts that are online, and then target those hosts for a SYN scan. So he or she is not going to be generating a large number of noise. So once again, we're trying to figure out whether or not an ICMP-based ping sweep occurred in this environment. So I will press the up arrow here, and I will take advantage of the statistics. I will say -Z, and if I just put any random value here, we will get the help for the statistics, right? We will talk more about some of these statistics as we go along, but the one that interests us right now is the protocol hierarchy statistics. So I will now replace this -Z here and say IO, PHS. Enter. The thing with this here is that, yes, you see this here, but if my screen was smaller, if the font was smaller, you would also see I have all of this here, which if you have a very large PCAP file, this is probably going to be distracting. It's going to be a waste of time. So what you want to do ultimately is come back here and put a -Q. Okay? And let me clear the screen. Actually, let me clear the screen first. Right? I'll come here, put -Q. And now I have just this here. Right? Notice I ran the TShark and I have just the protocol hierarchy. We don't have all of that other packet information that passed by before. So let's step back for 1 second. The team came and they said they believed that ICMP, a network sweep was basically performed against the infrastructure, right? This is the belief. We're trying to figure out whether ICMP was in use in the infrastructure. We can see here that when we looked at the protocol hierarchy, there are ICMP packets, which means at this point in time, we can continue with our analysis. If the team had said, you know, there's ICMP traffic we expect to see in this PCAP, and when you look here, you did not see any ICMP, you could have probably concluded maybe they gave me the wrong PCAP file, or maybe TShark did not understand these packets properly. So we will continue pressing ahead, because at this time, we have evidence that suggests that ICMP packets are in this PCAP file. Now, we can do this the simplest way, or we can do this the most difficult way. So we will look at this here now from different perspectives, because for some of you, one way might be easier. For another set of you, another way might be easier. So let's look at this from a couple of different perspectives. Now, let's go back to the cheat sheet. Remember, Stephen gave you the cheat sheet inside the chat, so you should have that. If we zoom in here, right, come here. Right. If we look here, we can see, right, we can see from the ICMP packet perspective, we have at offset 0, we have a type, and this represents 1 byte. We can also see we have at offset 1, and note where we're counting offset, we're counting from 0, right? So at offset 1, we now have a code. So from a stimulus and response perspective, if someone is initiating a ping on their end, it is more than likely they're sending me an ICMP echo request. So I need to find a type as well as a code that is representative of an echo request. So what I can do, if I scroll down here, right, we can come right here, and we can see we have a type of 8 and a code of 0, which says it is an echo request. So we have learned immediately what are the values that would be in the ICMP header that helps us to understand an ICMP echo request. Let's come out of here now and go back to our environment. Okay. All right, let's clear the screen here. And what I will do at the same time, I will split this screen here horizontally. I will increase this font here so that we can see the two different perspectives as we use them. Okay. All right. So the first thing we will do, we are trying to identify all of the echo requests. So we can now say TShark, we can say -N and -R again, and we give it a PCAP file that we would like to use. Okay. And in TShark, we have the ability to use either capture filter or display filter. For what we're trying to do right now, we will use the display filter. Later on, we will use the capture filter. So now we say, okay, what have we learned so far? To take advantage of the display filter, we would say dash capital Y. And we'll put our filter within quotes. Now, if you are on a Windows system, you are going to be better off using the double quotes, because the single quotes is more than likely going to trigger an error. So if you're following along, I'm hoping that you are following along from the Linux perspective rather than the Windows, because yes, you will be able to do a lot of this that we're doing, but in some cases, you are not going to be able to do it as easily as we will be able to do it in Linux. All right. So we've learned that we have the ICMP protocol that we would like to focus on, and ICMP has a type. And when we looked at the cheat sheet, we saw that a type of 8 is associated with echo request. And I will put this here in brackets. Okay. Along with that, we also learned that, let me put this in bracket also. We also learned that an ICMP, the ICMP protocol also has a code. Okay. And a code of 0 should give us all of our echo request messages, right? To confirm, we can go back here, right? If we go back here, remember, we have a type and we have a code. And if we come further down, right, we have a type of 8, a code of 0, and that gives us echo requests. So we go back now into our environment, and if everything goes according to plan, we press enter, we see now we have all of the ICMP echo requests, which means someone on the other end, right, was actually communicating with our environment. Note, in this example here, or throughout this demo here, throughout this session, we are using a relatively small PCAP file. 1, in the interest of time, and 2, to keep it simple so that everyone understands clearly what we are trying to achieve. But realistically, in a production environment, you are more than likely going to have a very, very much larger PCAP file. So some of the tricks I will add on now is going to help you in those environments that you have a larger PCAP file. So this is one way that we could have taken advantage of it. We took advantage of the fields within TShark, but it might be a case where you're using a different tool that might not have an ICMP type equal 8 or an ICMP type equal 0. So what else can we do? Let me here say cd. Let me go to bash first. Let me do cd TShark, and let me clear the screen. We will copy, let's say I copy here, and I will paste this here. Okay? I will put the quotes here. And once again, we would like to, remember, you should put everything in brackets. And whereas above here, I use 2 ampersands, at the bottom here, I'm just going to use and instead. So you can see that there are different ways to achieve the same objective.
Hey, Nick, you muted yourself. Nick, I think you muted yourself.
Sorry about that. I'm not sure how I muted myself there. Sorry, everyone. All right. So I was saying, let me go back here. What we're doing is, in this example here, we're still targeting the ICMP protocol. But what we're doing is we're looking inside, let me remove the square bracket. We're looking inside of the ICMP header. And where exactly are we looking? We're looking at offset 0. What is that offset 0? If we go back to the cheat sheet, we know offset 0 has the type. So we're looking for a type here that equals to, let's go back here, type here equal to, actually let's change this to 8. We're looking for the type that equals to 8. So this is basically the same thing as this. This example above here is just Wireshark or TShark in our example, making it easier for you. So we're looking for 8, sorry, what am I doing here? ICMP 0 equal 8, right? The type equal 8. And we're looking again for ICMP in the ICMP header, right? And we're now looking at offset 1. What is an offset 1? We can go back to the cheat sheet, and at offset 1, we have the code. Okay. So now we're at offset 1, and we're checking to see if that value is equal to 0. If everything went according to plan, once we press enter, let me just bring this in a little smaller. Okay, now we see that we have an exact match for the bottom here with the top here using 2 different mechanisms. Here, we took advantage of the specific display filter that has the ICMP type equal. Here, we're going into the ICMP header, and this here is going to be very helpful when you're using tools such as TCP dump, for example. But for us, we're using TShark throughout this process. So what have we done so far? We have identified that, yes, echo request was done against our environment. Now, as we look at that, right, we need to figure out a couple of other things. When did this activity start? Now, if we look at the time, right, if we look at the time here, where we would typically, or look at this location where we would typically expect the time values, it does not seem to make much sense to us right now. What we want to know is date and time. Think about it this way. Whenever you're doing incident response, whenever you're doing packet analysis, it is more than likely you need to be able to answer when something happened. Who, what, when, where, why, how. When it's going to be dealt with via the time. So what time did this activity actually occur? Let's look at it from 2 different perspectives again. I will just press the up arrow here, and I will clear the screen. Right. Okay. Where are we? All right, let me just run this command one more time here. I will just copy here. Actually, I will use this entire one at the bottom here. Let's use this one, because we could use either one. Just want to show you that there are different perspectives, okay? So we have that. Clear the screen. And now, let's figure out the time. If you are looking at this from a local perspective, we would say, show me the time from the local perspective. I will say -T, and I will say, show me the time from the local perspective. This is what the -AD will do, right? Now we can see, let me reduce the font again a little bit. Right, now we can see we have better information as it relates to the time. Reduce the font. If you cannot see the font clearly, let me know so that I can increase it again. But here we now see clearly when this activity occurred. Okay? We now have a much better view as to when this activity occurred. And whereas we took the time at the top here in local, let's look at it now from a UTC perspective. Why? Because in large enterprises, you are more than likely part of a global operation. And if you're part of a global operation, you might be correlating activity in packets across different time zones. So what we can do is say -T, and we will use the UTC time. Okay. So I press enter. Let me reduce the font again, just so that we can see clearly. All right. Now we have the top in local time, right? And we have the bottom in UTC time. So we have addressed the concern so far whereby the senior cybersecurity folks came to us and say, hey, we believe, let me rephrase that, we would like you to do some threat hunting to confirm or deny our hypothesis, or basically to prove or disprove our hypothesis. That hypothesis being, it's muted. Can you all hear me clearly? I'm not muted. Can everyone hear me clearly? Just give me 1 second. Let me check with Stephen to see if he can hear me. Can you hear me? Okay, thanks. I'm not sure why I saw the message here about being muted. All right. So I was saying that if you're correlating activity across a large number of PCAP files in terms of your organization is global, then you will be able to use UTC to coordinate the time, right? Rather than local. If you're in a local time zone where all of your packets are there, then take advantage of the local time. And for those that said you did not hear, you did not really miss much. Okay, I just repeated everything there. We were just talking about time. Now, once again, this could have been a very large PCAP file. So if this was a large PCAP file, how would we find the various sources that have been targeting our environment? Let's clear the screen. And now let's take the same command here, right? I will remove the time. And I will say, actually, you know what? Let's leave the time. All right, let's leave the time. And when we look at these packets here, we can take advantage of additional tools now. Tools such as awk, such as cut, all of these different tools. So let's do this. Let's say, we press the up arrow, and we now pipe this output as in this content here. Rather than showing it on the screen, we're going to send it as input to another tool. Basically, we take the output from TShark and use it as input to another tool. So the tool we will use now is going to be awk, right? And with awk, we need to use a field separator. I don't need to specify a field separator by default, but I'm putting this so that you can understand how you can specify your separator. For us, the separator is going to be a space. Why the space? Well, if you look here, you can see there's this field. We can see this field, right? And all of these are separated by space. So the space is what is going to be used as the field separator, or some other tools might call it a delimiter. Okay, so for us now, let's go ahead and continue with awk. Now, once we've specified a field separator, we now need to tell awk to do something. So I will put this in quotes, use these curly brackets, and I'll say, awk, I need you to print. Well, what is it I need awk to print? I need it to print, let's count, 1, 2, 3, 4. I needed to print the fourth field because the fourth field represents the source IP of where this traffic is coming from. So I will now say $4. Okay. And we can see now we have the source IP. Yes, in this example, we have only one source IP. But remember, we're talking about a situation where in your enterprise, you will have more than likely a larger PCAP file with this type of activity, as well as from a demonstration perspective, we're trying to keep this simple so that everyone is clear on how to understand it. So this is why we have a much smaller PCAP file. So let's continue building on the assumption that this was a large PCAP file. Now, if it's a large PCAP file, we need to figure out what are the IP addresses that are in use, what is the frequency of these IPs communicating in our environment. So what I will do, I will type this here, and I will say, rather than giving me this output on this screen, I would like you to instead sort it, right? Because sort is going to organize everything for me. And when you sort it, then take the output from sort and put it into unique so that I can see those unique values. At this point in time, we see there's only one unique value. But what about a situation whereby you have that very large PCAP file with tons of ICMP traffic, right? Echo requests. What we can do here now is give me a count of those unique values so we can see the frequency of their occurrence, right? And here we can see that there were 5 occurrences of IP 10.00102. Now, we could even build on this a little further because, once again, you are in a large enterprise. So what you might decide is, I don't want to see a large set of information scrolling by on my screen. What you should do instead is show me just maybe the top 5 or the top 10. So in this case, we only have 1. So just to show you how you would use that command, I can press the up arrow and I type this output here into the head, and I can say lines show me 1. And it's going to show me, in this example, there's only 1, right? Similarly, if I wanted to see the least used entry, I could have said tails. I could have said tails. Okay. Sorry, not tails, but tail. okay? And I see the last entry. So you can see immediately how we are able to find this information and so on, okay? Now, based on what we have so far, we are now able to go back and tell the team that we have some insights. But before we do, because remember the hypothesis is a ping sweep accord. But we only know so far that this source targeted our environment. We don't have anything else. So let's go back for a second, right? And come here and figure out, okay, what was targeted? As you can see, we see 103, 104, 105, 106. This sequence suggests that it is more than likely some type of sweep going on in our infrastructure. So what we can do now to wrap this up, or to wrap up this first part, let's actually go back here, right, to this command we ran before, remove heads or head, right? And in this example, we cut field 4, right? Because we counted 1, 2, 3, 4. But we would like to get now the destinations that were targeted. So we would now count 5, and this would be 6. So if I now change here from 4 to 6, right, we should now have the destinations that were targeted, and we see that all of them were targeted one time with one ping. This is going to become important shortly because this to me suggests that the threat actor is not using a native operating system, but we'll figure that out shortly. But for now, what do we have? We are able to answer the question that the senior folks came to us with, the hypothesis. They came and they said, hey, we believe that a ping sweep occurred against our infrastructure. We wanted you to prove that theory or that hypothesis, or disprove that hypothesis, whether or not someone actually performed a ping scan against our environment. So we know, with our excited self, thinking that, we're new on this job, we are able to prove the theory on the first day, go back to the team and say, hey, here is what we have. But the team said, hey, man, that is cool. I really like what you did there. But guess what? We have accepted the risk that once we have assets on the internet, someone is going to be scanning them. So we really don't care about that. What we are concerned about is hosts that are responding, stimulus and response. If you have a device on the internet, it is more than likely someone is going to ping it, someone is going to perform a port scan. So we're not concerned with that. We've accepted that risk. Help us understand the hosts within, or the hosts within our infrastructure that actually responded back to these echo requests. Now, this is a bummer now because, we thought that we answered the question. We proved the first part of the threat hunt, and we thought that was all that was needed. So we have to go back to the drawing board now. So let's try to figure out how we learn about those hosts that respond. If we come back to our cheat sheet one more time, right, we can see, once again, we have the ICMP header. And as we look here, remember, we have the type, we have the code. And from a stimulus and response perspective, if you've ever used ping, right, PING, you would know that when I send an echo request, I should probably get back an echo reply, providing that no firewalls or anything were blocking that traffic or the packet was not lost. So as I look here, right, I can see we have a type of 0 and a code of 0, and I see echo reply. All right. So now we're able to figure out which host replied to the network sweep or to the ping scan. So we go back now to our TShark environment. First thing we do, first thing we do is look at it once again from two different perspectives. I will clear the screen, right? I will press the up arrow, and I will change here, because we will use the one at the bottom also, change here to type, and I will change here to code. Okay? And if we come back to the cheat sheet, we're looking for type 0 and code 0, right? Here we are, type 0, code 0, echo reply. So I will say now type 0, right, code 0, boom. Let's remove the time because we already answered the question on when this activity started. Good. So now we see from the stimulus and response perspective, we have the echo replies. So far, so good. And remember, we are doing this from two different perspectives so that you can get the necessary insights. So using the second mechanism, I will just press the up arrow and change here from 8 to 0. Right? Remember, ICMP 0 means we're looking at the first offset, the 0 offset inside this packet. And we will see a little bit more about these offsets shortly. Then we're looking at ICMP 1 for 0. And once we get matches, that should also be the echo reply. Enter. Boom. Now you can see we have the echo replies going back. So we are confident now that hosts within our infrastructure actually responded, right? So let's try to figure out, similarly to what we did before, what are the unique hosts? Obviously, we can see from here what those hosts are, okay? But it could have been a case whereby all of these hosts did not respond, or more importantly, you have that large pcap file and you now have to figure out from that large pcap file, what are the unique hosts, what is the frequency for their response, okay? So let's pick on the command line kung fu tricks that we learned before. And for example, in the SEC 503 class, on days 1 and 2, especially day 2, I believe it is, we talk a lot about command line kung fu, using these tools to do packet analysis. And later on in the class, we talk about using them for log analysis also. Okay? All right. So what we will do now, we will use awk again, and we'll tell awk we would like to use a field separator. Note in this example, I'm using the equal sign. In the previous example, I did not use it. Once again, showing you different ways to achieve the same objective. And what do we want here? We would like to print, right? We will put this in curly brackets. I will just put a space for my own convenience. I say print. And which field do we want to print? We want to print the field that is associated with the source IP. The source IP being not the threat actor's IP, right? But the source IP being the IP address for the host responding in our infrastructure. So we can actually say here, let's say this would be field 1, this would be field 2, and this would be field 3. These are the hosts responding. So I would say 3, right? And now we have these fields here. Now, whilst I showed you it that way, there is yet something else I could have done to make this a little bit easier for you. For example, I can clear the screen here, right? And I can, let's say, copy. And I'm copying just to show you that, actually, you know what? Let's do it a different way. So when we run this here, we have the echo replies, right? But we're trying to extract the fields of the host that responded. Now, in this example at the top here, I deliberately did not put in a particular information, but I will put it in at the bottom. And here's why. Remember, we're looking at the stimulus and response, and you have a situation where you have a very large pcap file. Okay? You have a very large pcap file. So what you should have done instead is, along with this here, you now say, and, right? And we can say, and the destination represents the threat actor's IP, which is 10.0.0.102. So let's copy this and paste, right? And now we would have traffic that is going directly back to that threat actor, because our concern is only with 10.0.0.102, not with anything else. Now here, we extracted the fields, right, of the destination by taking advantage of awk. But could we have done this a much simpler way? Absolutely. Let me clear the screen, press the up arrow, and now I will say instead of what we just did, let's take a different route. Let's say now -T. And when I say -T, I would tell TShark, I would like you to use the fields. And which field would I like to use? I use the -E first, and I tell it I would like to use the IP.destination field. Okay? And I plug this in, and you can see that I have the same results here that I have here. The only difference is now I can pipe this into sort. I can pipe this into unique and get a count, right? And if I wanted, I can sort numerically and get statistics from the largest number to the least number, right? So now we have, once again, the destination is 102, right? 5 packets went there, but what we should be more concerned with at this point also is the source. Because remember, the ask from the senior team is which host or hosts responded. Okay, so let's do that now. Boom. So here we have, once again, right, we have all of these hosts that responded to the threat actor's stimulus, the ICMP echo request. Now, so far, the second part of the question was which host responded. I think that at this point, we are in a position to be able to answer that question for them. But before we do, let's just do a couple more things. Let's clear the screen here, right? And what we will do, let me show you a couple of quick cheats. So we could have instead, when we wanted to look at these ICMP packets, I could have instead, rather than going through all of that, I could have just said ICMP. Sorry. Right? And this would show me all the ICMP packets. But you can see here we have destination unreachable, port unreachable. We have reply, we have request. We wanted to stay focused on the specific hypothesis first, whether or not ping sweep occurred. We knew that from the echo request. Then the second part of the hypothesis was whether or not any host responded. And we were able to answer that part of the question also. But this here is just now some simple cheats. So let's prepare to wrap this up so we can go and give the senior team the necessary guidance that they asked for. So let's write a command. Let's say actually, take the same TShark. And what I will do, actually, let's leave this one at the top and use the one at the bottom since some of this has already been built out here. Okay. So we have here, let's say the fields, let's say we have the field source, source IP, right? And we would like to know the destination, IP.dst. Every time we wish to add a field, we specify the -e, and then we specify the field name, okay? Every time we would like to add a field, we specify the -e, and then the field name. So what else would we like to do now? We say maybe we would like to add the frame time, okay? So we have the IP, the source IP, we have the source IP, we have the destination IP, we have the frame time, and let's wrap this up by putting the -e again, and we say ICMP.type and the ICMP.code. Okay, we press enter, we see we have this information returned, and let's put the time at the beginning for simplicity. Let's move the time from here, and let's put it instead here, -e, frame.time. Okay, clear the screen. So now we have this here for simplicity. Now, you might instead decide, you know what, these guys or gals in that senior team already are busting my chops because I give them the information they asked for, then they sent me back to do more. So I'm going to wrap this up, and I'm going to give them everything I think that they need. So these guys and gals also might be taking advantage of other tools in their environment. Maybe they're doing some statistical analysis, maybe machine learning, whatever it is. So they might instead prefer, if I give them this guidance as a CSV file that they can then use to import via pandas or some other mechanism. Okay, so let's now say, okay, what we will do, we would like to use this as a CSV file. So rather than this output, and actually let me copy here so you can see the difference with the two. Right? So I will paste here. Right? So rather than showing the output with this tab or this space here, by default is the tab, right? I will say -e, right? And what I would like to do is put the headers. So I will say header equal Y. What will happen is the headers will now come above here. So these are the headers like the frame time and so on, the source and destination IP, this will come. So when I press enter here, you see now we have frame time, IP source, destination, type, and so on. But along with that, remember we were saying that these guys and gals might want to use this as part of their analysis, where they might be using pandas, or maybe they want to use some type of machine learning, whatever it is. So I'm going to just try to get rid of them by saying now -e, and I will specify a separator. The separator I will specify is comma. So I'm making this now comma separated CSV file. And I will now write this here to a file called, let's see, threat hunt ICMP.csv. Right? I will now cat threat hunt CSV, and now we have the output here. And I can now feed this to those guys and gals on the senior team, and our solution should be addressed here. We now have addressed their two primary concerns that they ask us. So we gone now, you know, we go with our excitement, hey, I'm happy to report that not only did we find initially that ICMP reconnaissance was performed against our infrastructure, but I've also identified the hosts that have responded. And here I've provided the guidance to you. We can see the echo replies going from 103, 105, and so on to this destination, right? We know it's echo reply because we have the ICMP type, which is 0 here. We have the ICMP code, which is 0 here. Boom. So we think we're finished. The guys and gals in the senior team look at us and say, man, I really like what you're doing so far, but unfortunately, this is not the end of the road for us. What we need you to do now is profile the threat actor. What I need to know is whether or not this threat actor fits within our threat model. Basically meaning, are the tools or the tactics or the techniques that this threat actor using, are they fit to our threat model? Should I have a concern with this? Now, this is a bummer because we have to now figure out what is it that this threat actor is using. Well, let's see if we can learn a couple of things as we go along here. First up, let's take one of those packets, those ICMP packets, and we will focus specifically on the request, because from a stimulus and response perspective, if I send you one packet that has the string sans SEC 503 inside, then you should respond back to me with the sans SEC 503 inside that same packet, because it's a stimulus and a response, in this case, basically an echo request, echo reply mechanism. Whatever I send you, you should send me back. So let's press the up arrow here and find those echo requests, right? Let's see. Okay. Let's find these echo requests. And we will only take, let's say maybe we take one echo request, right? And I will say -x, and I will pipe this into, actually, let's keep this even simpler. Let's take advantage now. Let's take advantage of a different filter. Let's put this here in brackets because we would like to have these two together, right? And I will clear the screen at the bottom here to remove any clutter. Right. Now I will say what I'm looking for is, right? I will say I'm looking for a particular frame. Let's say we take frame 239. So I will say frame.number equal 239. Okay, and ICMP 0 equal 8 and ICMP 1 equal 0. Clear the screen, press enter. So we have this one packet that has been returned. But this in itself does not help us answer the question in terms of how we profile the threat actor. So what I will do here, I will press the dash, put the -x, lowercase x, I will clear the screen, press enter. All right. What do we have here now? We have the raw hexadecimal of the traffic that is being seen on the wire. Okay. Now, if you remember, I said before when we spoke about capturing traffic on, right, when we spoke about capturing traffic on any interface, I said that it inserts a fake header, not like an Ethernet header, but a fake header. And this header is 16 bytes. Now, how do I know this is 16 bytes? Well, you can look at the TCP dump page, has guidance on this protocol header. But more importantly, these 16 bytes here, starting at offset 0, right? We can see that the next row starts at 10. This 10 represents 16. This 20 represents 32, which means each one of these rows here represents, 16 bytes. Okay, each one of these represents 16 bytes. Now, along with that, from the protocol information, what I know, this here represents what is called a protocol type. If you're using Ethernet, you might have heard about the Ether type. This is the protocol type. And this protocol type 0800 means that IPv4 is coming next. And from an IPv4 perspective, what I know is this is version 4, and this 5 tells me the length of the IPv4 header, right? So I would have to multiply this 5 here by 4, not because it is version 4 here, but I would have to multiply this by 4. If you really want to get to the depths of understanding how we get there, hang out with us in the 503 class. We go into this in much more details. So I have the header length that is 20 bytes. So the IP header would be from here, right? And this is 16 bytes. This would be 17, 18, 19, 20. What is coming beyond the IP header? If I look at offset 9 within the IP header, it will tell me what is coming next. And offset 9 here says that ICMP is coming next. How do I know that? Well, if I do cat, let me clear the screen here, etc protocols, right, and I say more, right, we can see as I look into that file, 1, right, represents ICMP. So I know that at offset 9, and once again, in 503, we go deep into each component within this header. But as I look at offset 9, I know this is ICMP coming here. Okay, now we already know that the IP header is 20 bytes. The ICMP header is 8 bytes. So we can now come here, right? This is 16, 17, 18, 19, 20. And here represents the start of the ICMP header. And we have 1, 2, 3, 4, 5, 6, 7, 8. Those represent the 8 bytes of the ICMP header. And remember, we were looking for ICMP 0 equal 8, which is this value here. Similarly, we were looking for ICMP 1 equals 0, which is this value here. So we actually tested these 2 bytes at first. Okay. Now, the problem here for me is that as I look here, I don't see any payload. So I cannot infer immediately whether or not some particular tool was being used. So what do we do next? Well, the question the team asked us is that they want to know whether or not the threat actor was using a Windows device. They want to know whether the threat actor might have been using a Linux device or whether the threat actor was using some particular tool. Now, this is going to be a bummer for us because we might not know how these operating systems operate. No pun intended. So let's try to figure this out together. Now, let's instead do, let's say, TCP dump, right? And we will capture once again under any interface, right? We say interface, we say -n, interface, any, and now I will use a capture filter. Remember previously we used a display filter where we used the -y, right? Let me bring this up here. Previously we used a display filter. Now I'm using a capture filter, okay? And I will say ICMP, okay? So we're capturing now, and more specifically, I just would like to capture 1 packet. And in capturing that 1 packet, I would also like to see the hexadecimal output of that packet, okay? Let's do this. Capital X. Okay. Press enter. Sorry. Thinking TCP dump. Capital lowercase x. Okay. And now let's do a ping. Let's say ping. Let's ping to a Windows device 10.0.0.1. Okay. And I will say now before it ping, remember when we looked at the information before, we saw all of those requests and response had 1 entry. Now, I know that by default, and let me break this out here before we do any capturing. I know by default on Linux, when I ping, the ping will keep going consistently until I stop it. Now, the reason you don't see any response here is because maybe the firewall is blocking the traffic on the end. But I'm not concerned about the reply. I'm concerned about the request. Because from an echo request response, echo request reply mechanism, whatever I send you is what you are going to send me back. So I'm going to break out of here now, right? And I will now come back here, run this again. And in this example now at the bottom, I will instead say, you know what? I just need you to run 1 ping, okay? Just 1 ping is what I want. So I will say -c, sorry, 1, and I press enter. And we can see here now, actually, let me do it a different way. All right. So we can see here now we have that fake header and so on again. But more importantly, we have from the ICMP packet perspective, right? We have the IP header, right? And remember, we said 20 bytes. Remember, each one of these rows here represents 16. So here is where the IP header ends, and here is where the ICMP header starts. And we know that the ICMP header is 8 bytes. So we have 2, 4, 6, 8. Now we have all of this additional bytes. When we looked at, let me bring up this one here. When we looked at this before, let's say we did TShark -n -r, let's say nmap, and let's say ICMP that type recap dash y. Let's say ICMP.type equal 8 and ICMP. But in this example, I'm not putting the brackets, but you should make it a habit of putting the brackets. Okay. Minus x. Let's see. And frame that number, I believe we said, equal 239. Right. If we look at this here, the ICMP header ends and there's no data beyond that. Here, after the ICMP header, 2468, right, we see a lot of data here. I believe this is 56 bytes of data. We can figure out that later on, or come hang out with us in the 503 class, as I said, where we get deeper into this. But we can already see one anomaly. That anomaly being, when I ping from a Linux device to a Windows device, I have payload that looks like this. Whereas in the PCAP file, there is no payload. So what I know immediately is that this is more than likely not a Linux device that the threat actor is using. Now, could it be that the threat actor is using a Windows device? Let's test that theory again. Let's come back here now and let's run. Let me copy this here. Just keeping it simple with the copy and paste, right? And let's bring up a Windows device. Actually, before we do, let's do this. Let's say IP address show. We can see that this IP address is 101. So we need to ping 101, okay? So I'll clear here, run this again. And over here, I bring up a Windows device, okay? And on that Windows device, let's now try ping 10.0.0.101. I will say, now let me break out here, just for explanation's sake. Now, remember we just said that in the Linux environment, right, it pings consistently until I tell it to stop. We know that when we looked at the PCAP file, each one of those pings had one. So is it a case that Windows only send one ping by default? Let's test that theory, right? We're seeing that Windows is going to send or sent 4 pings. So that in itself also tells me the threat actor is more than likely not using Windows. But let's further confirm the theory, okay? All right, let's come back here, clear the screen. Press the up arrow. We're going to capture one packet. From the Windows perspective, we will do this. So we say -n, and we only want one packet to be captured. Okay? Or we only want to send one packet. So we send this one packet now, and we look at Windows. We see, similarly to Linux, right, beyond the ICMP header, right, we have 2, 4, 6, 8. Beyond the ICMP header, we have a lot of data. Right? And notice in Windows, we have what seemed like something to do with the alphabet, A, B, C, D, E, F, G, and so on until we get to W, and then we start again from A. So immediately we are telling ourselves, okay, the threat actor is not using Windows or is not using Linux. And we can confirm this by, once again, if we look at the PCAP file, let me just clear the screen. Actually, we have it there. Let me just copy here instead. We already looked at the Linux output, so we know what that looks like. Let's compare what we have here with the Windows. Right? So here, the threat actor does not have any payload beyond the ICMP header. So at this point, my conclusion is that no Windows or Linux device is being used. And when I say that, I mean the built-in features, the built-in ping utility. So it has to be that the threat actor is using some type of tool. But how do we figure out what tool it is? Well, the reality is on most days, any threat actor or anyone performing a network scan is more than likely going to be using a tool such as Nmap. So we can actually confirm or deny that Nmap was actually used. And if we do, for example, and we're preparing to wrap up here, okay? If we do Nmap help, right, and we scroll up, we can see from the host discovery perspective, let's go up. From the host discovery perspective, scan techniques, we can do a ping scan and disable port scan. Remember I said the threat actor is more than likely going to perform a ping scan before he or she performs a port scan. So we have the ability to do that. So is it that the threat actor actually used Nmap to target our environment? Let's test that. Let's say we do, once again, and let's actually bring this up here so we know what we're comparing against. right? And at the bottom here, we will run nmap. I will now say, let's say nmap, and we say we want to perform the ping scan. Now, we would like to perform the SYN scan again, the ping scan against 10.0.0.1. The ping scan, not SYN scan, the ping scan against 10.0.0.1, which is the Windows device, right? And when we're on the local network, by default, the way we're using nmap here is going to try to send out ARP to learn about whether or not this host is online. So we would like to instead tell nmap to just send IP, okay? So let's go ahead now and capture one packet from this here, okay? Let's send nmap. Okay, now, as we look at this here, right, nmap is probably going to come back with the host is online or something like that, but that is not the major concern for us. As we look here for the results that has been returned, we see beyond the ICMP header, there is no packet, right? No data, I should say, which ties in to what we have above. Let me do this a different way to make this a little bit clearer. Let's split the screen here vertically, right? This is the last thing we will be doing before we wrap up. All right, so I will press here, and I will, let's say bash, all right? And let's do TShark -n. We just do this here. Keep it simple. Okay. All right, that's going to be too small. So I will just go back to what I had before. I don't want to make it too small that you can't really get the gist of what is going on. Okay. All right, let's prepare to wrap this up here. And we can see, once again, good. So yes, as I was saying, so beyond the ICMP header, we really have no data. So I believe at this point, we have answered the question that the team asked. The team said, okay, first they asked us to prove or disprove the hypothesis that ping sweep accord in our infrastructure or against our infrastructure. We answered that question and say, yes, ping sweep accord from the host at 10.0.0, I think it's 10.0.0.2 or 102 or something like that, right? Then when we provided that guidance to them, they came back and said, nope, we need to know which host responded to the echo request with an echo reply, for example. We went back and we gave that guidance. Then they came back and they wanted us to profile the threat actor to see how the tactics and techniques fit with our threat model. So we can now go back and say, okay, what we've learned is that the host at, let me bring this up here so we can tell the story. Move this here. So we can go back and we can tell the story. We can say, hey, you know what? On February 11, February 11, 2018, around 15:55 local time, right? The host at 10.0.0.102 targeted various hosts within our infrastructure. The host that responded to the echo request with echo replies, basically 103, 105, 106, 90, 104. Upon further analysis, and via some threat profiling, we've learned that it is more than likely that the threat actor was not using Windows. And when I say Windows, I'm talking about the built-in Windows ping tool or the Linux built-in tool. What he or she might have been using was nmap to target our environment via active reconnaissance. Okay, and that basically represents today's session. Do we have any questions?
Hey, Nick, thank you, man. This was fantastic. I've seen a lot of comments throughout the session today, but haven't quite seen any direct questions. But fantastic work here, man. Lots of gems shared. Really appreciate you.
Okay. All right. If there are no questions, you know, we're going to close off this session shortly. But if you have any questions later on, feel free to reach out to me. Thanks, Justin. Thanks, Jaskamal. Thanks, Mohammed. If you all have any questions, thanks, Matt. If you all have any questions, feel free to drop in later on. I'm open anytime. Hopefully I will see you all in one of the SEC 503 class, where we go into much deeper analysis here. But do note, this is part, as I mentioned, of a 9 or 10-part series. The next one is probably going to be next week, Tuesday or Wednesday, around the same time. And we will move from the network layer to the transport layer, where we now detect like the SYN scanning and what else might have occurred within the environment. And then we will continue building on that, detecting the attacks, performing analysis on exfiltration, packaging as in archiving and all of these things that as part of the full attack cycle, exfiltration and all of that we will take a look at later on. So this is, as I said, part of a 9 or probably a 10-part series where we will be focusing on packet analysis for network forensics, help you to understand a little bit more as you prepare to take advantage of the SANS SEC 503 or any other similar class within SANS that leverages packets for analysis. And to be honest, as we say in the SEC 503, packets or it did not happen. Basically, show me the packets, right? Hopefully today helped us to understand a lot more on how we can detect reconnaissance. Basically, one of the first steps that a threat actor would more than likely take if he or she is going to target your environment.
Thanks, Nick. And for everyone watching, go ahead and make sure you're following the SANS Cyber Defense page, or hop on over and subscribe to our YouTube page. All our lives will show up there. We'll have Nick's series coming up here on both pages in a bit. So look out for those posts. Make sure you're following us on social. And thank you so much.
All right. Have a great day, everyone. And once again, thanks for hanging out with us. Very much appreciate a couple minutes of your time. I went about 7 minutes over, but appreciate you hanging out with us. Okay.